Hi everybody, this is Bharat and I am recording my course project for the Machine Learning Foundations for Product Managers. And here I'm going to start off with the objective for this project, which was to predict the hourly electrical energy output of the combined cycle power plant. And we had with us the provided ambient variables, that was the temperature, vacuum, pressure, and the humidity. So basically there were two major tasks. That was the first one was to determine which type of machine learning approach was needed. The task was for us to try out different machine learnings using different tools. So I did it using Excel, Python, and AutoML, but I'm just going to show the Excel work here because this needs to be fit in the time frame. And I'm also going to quickly run over some codes in Python, but not and show the results what I got, but I won't completely go into detail of what happened there. But yeah, so the two major tasks here were to determine the type of machine learning approach that was needed and what were the best possible features we wanted to use to test this model, and also identify the different algorithms we might want to consider. So moving on, this was the raw data that was provided to us. This was the combined cycle power plant data that was provided to us. And as you can see, the data set is relatively small. So the approach that I wanted to use initially was to have the data on a 60-20 split, 60 for training, say as a 20 for validation and 20 for testing. But I think with that, the approach changed due to the lack of the data that was provided to us and lack of the amount of data that was provided to us. And as you can see here, I'm going with 80 split, 20 split. The first approach, it's very simple, building a regression model, considering all four hyperparameters or the input variables. And the model will be validated based on accuracy of the fit, that is R square, and also the root mean square error value. So we performed the regression for the first training data with all the four input variables and PE as the output. And as you can see, the R square was pretty good. It was a pretty close fit to the model. And we got around 92% accuracy or R square value of 0.929. And this was the ANOVA results are also pretty good. The significance of all the four variables being interactive and also all the four variables being equally statistically significant was validated by the F value being very, very close to 0, the significance F value. And let's look at the p-value for each of these variables, and which shows that they are less than 0.5. And we took a 95% confidence interval. And so that means that, anything less than 0.05 suggests that any p-value that is less than 0.05 suggests that that particular variable is very significant for the output result. And here we can see that the atmospheric temperature, vacuum, the pressure, and the relative humidity, all of them are less than 0.05, and which should basically say that it was a pretty good model to begin with. Let's actually now take this value, and here are the intercepts for the values we got. Here are the intercept values that we got, and also the coefficients for the various input variables. And we're going to input this particular coefficients and in our model, and like we'll use the model y hat is equal to, or y predicted is equal to the intercept plus coefficient 1 x1 plus coefficient 2 x2 so on, and figure out what exactly the predict value is. So moving on to the test data here. This is a 20% of the test data, and you can see, I have calculated, I have added additional columns here, which basically suggest which basically are the predicted PE values. The predicted PE values are obtained from the formula that I talked about, the intercept plus the coefficients into the input variables. So we'll use the model y hat is equal to, or y bar is equal to the intercept plus a1 x1 plus b1 x1, or a1 x1 plus a2 x2 so on. So these are the predicted values, and these are the original P values for the test data. This predicted value is based on the equations and the coefficients got from our regression analysis that we previously did on the training data. And looking at this, the values are pretty close. Let's take a look at some of the values. And they are pretty close they are very, very close for some values. But I also plotted just to show that there are outliers in this data, and we need to be careful in how we handle these outliers moving forward. For this analysis, I have considered outliers. For example, you see this absolute error of 43, 43. So basically, when you subtract the predicted P from the actual energy, you see that there is a huge, huge error. But that comes out as an outlier. So when you actually present it with a box plot, you will get to see that, okay, you might want to reconsider why these outliers are there, or when you're actually in real life conditions, what do you have to do about these absolute errors or these outliers are to check these conditions and see what exactly happened. There might be some environmental variables that we have not considered in these analyses which are impacting this model, and that is something that we need to consider when we do deeper machine learning or deeper data analysis on some of these data points. Right now, these are very controlled variables. What we have right now, we have no control over the environmental variables. So if outliers do come up, like the one we are seeing right now, it's very important for us to check those data points and see why those outliers are being presented. And we need to do a much deeper introspect on the and analysis on it to see like if there are other variables or if there are environmental variables that we have not considered. But now running quickly over the data, the root mean square error for this is what we're validating our model on. So it was around 4.66. The mean absolute percentage error was around 0.8. The um, the mean absolute the mean absolute percentage error and the mean absolute error was around 3.6, and the mean square error was around 21.37. So the root mean square error is relatively low for this model, but we have to, for us to be absolutely sure this is the best model or this is not the best model, we need to do a quick validation of what the other model also tells us. So, but I also did go ahead and actually plot the predicted value versus the actual predicted PE versus the PE, the actual PE versus the predicted PE, and also it looked pretty linear. So when the correlation between the predicted PE and the actual PE is pretty linear. So when you actually it's a pretty strong model. You can see the intercept is almost like when you take it's almost a straight line, y is equal to mx plus c, and the r square is also pretty strong. There's a pretty strong correlation between the predicted PE and the actual PE. So it's good to say that this was a good model, and this is a good approach to actually take. But let us move ahead and take the next model and see how those values have come up. So so what is approach two? Approach two is basically building a regression model considering all three hyperparameters or input variables. We are going to remove the relative humidity, and we are going to just calculate using the vacuum, atmospheric temperature, and the pressure. And we're going to use the same outputs, that is the R square, that is the fit of the model, and the root mean square error. So for the same thing, we saw that the R square was a little lower for this. It was around 9.91 or 91%, and but still all of the values did come significant. So it still holds good, and that is what we saw earlier too. Each and every variable was actually very independently they were significant and impacted the output. So that is a good analysis. But when there are interactions, it's good to consider the interactions also. And now we see that, and that is what we do in experimental design. But let's now focus on what we have on the three variables. On the p-value, all of them are very close to 0. So that basically says that all of them are significant and impact the output. And now applying the same intercepts and same method to test data, what we see is we see we calculated the same value, and the correlation was 95 here, and there we saw, like, it was around 96. And when we plotted the predicted PE versus the absolute PE, the R square is a little lower. It was 92.92 there, and there's 0.91 here. Like I said, it's a little lower, but again, still very, very close, pretty linear when we do when we plot predicted PE versus the actual PE. And the absolute error here also we see an outlier, which again tells us there is something weird going on with that particular data point. Maybe there is an environmental variable that we need to consider, or maybe we need further analysis on this. So, okay. Let's take a look at how it stacks up, how these two models stack up. The RMSE, the root mean square error, is a little larger here compared to the first model, and when you see the mean absolute error and the mean absolute percentage error also is a little higher when compared to the other models. Yeah. So finally, going to the conclusion. From the results, approach 1, a regression with all factors inputs provided a better model with better predictions. And now, just comparing the values, you see that model 1 had a better correlation, had a lower MAPE, lower MAE, lower root mean square error value, and overall lower mean square error. So that's about this. I just want to